Welcome to AI Paper Podcasts, where we break down dense research into, well, knowledge you can actually use. Today, we're tackling something pretty big, not just an incremental update, more like a foundational shift. We're diving into Pedro Domingos' paper, Tensor Logic, the language of AI.
Yeah, this one really hits on a sort of historical irony in AI, doesn't it? I mean, here we have this field changing everything, but it doesn't have its own language.
Exactly. That's the really startling idea here. Why are we still using these, general-purpose tools? Think about other huge fields. Physics really took off when Newton gave it calculus, right? Digital circuits. Yeah. They had Boolean logic. They found their lingua franca.
And AI. We're building these multi-billion-dollar models with Python, which, was never designed for AI. And then we layer on libraries like PyTorch or TensorFlow. Now, they're great for autodiff, getting stuff onto GPUs, absolutely. But they offer basically zero built-in support for, core AI tasks, things like automated reasoning or automatically acquiring knowledge.
And if you look back, the old symbolic AI languages, so LISP, Prolog, they were actually pretty good at logic, at knowledge representation. But they just couldn't handle the scale we need now. And crucially, they weren't built for learning from massive data sets. It really does feel like trying to launch a rocket using, spreadsheet software.
That's a perfect analogy, yeah. We're stuck in this world of compromise.
Okay, so let's nail the core insight right now for that quick summary people might want. What's the mission of this paper?
The mission is basically to propose Tensor Logic. This is positioned as the unified language for AI. And the key insight, the really big one, is that it merges neural and symbolic AI. It does this based on a, frankly, radical mathematical observation that logical rules and this operation called Einstein Summation, or Einsum, are mathematically the same thing.
Wow, okay, so the entire structure needed for any AI system, symbolic or neural, is just the tensor equation.
That's the claim. One core construct. And because of this unification, Tensor Logic can supposedly describe everything elegantly. Simple perceptrons, formal logic, complex transformers, graphical models. But maybe the biggest promise, the real payoff they're aiming for, it's enabling sound, transparent reasoning directly in embedding space, combining neural network scale with symbolic reliability, and potentially, finally, offering a real cure for things like LLM hallucinations.
Okay, that potential hallucination cure is huge. We definitely need to circle back to that. But let's stick with the basics first. The paper argues pretty strongly that just sticking with Python and libraries is, inefficient. It calls trying to add symbolic features a long and costly series of hacky attempts. So why can't we just keep iterating on Python?
Well, fundamentally, the language itself doesn't really share AI's core goals. The paper lays out these 4 requirements, desiderata, for what AI's true language should do. First, it needs to hide everything that is not AI. You shouldn't be fiddling with memory management or, low-level stuff. The focus should be purely on knowledge and learning.
Makes sense.
Okay, second.
Second, it has to natively support adding prior knowledge and doing automatic reasoning right from the start. This is where symbolic AI always shone, right? Defining facts and rules.
Right. And the third point tackles this trust issue we have now, doesn't it?
Exactly. Transparency and reliability. Models need to be explainable, not just black boxes. And finally, number 4, it has to scale. Effortlessly, ideally, on modern hardware. To get all 4, the argument goes you can't just bolt things on. You need to merge the underlying math. Symbolic AI's knowledge and transparency with deep learning's learnability and scale.
It sounds very neat, very elegant. But, symbolic AI and deep learning feel like such different beasts. Yeah. How does Tensor Logic actually bridge that gap? What are these foundational observations you mentioned?
Right, this is where the cleverness comes in. Observation 1. Tensors and relations. Think about a simple logical relation, like parent, Bob, Charlie, that's a fact. In Tensor Logic, this fact isn't just a statement. It's a compact way of representing a sparse Boolean tensor.
Booleaning. It's all zeros and ones, true or false. Precisely. Imagine a huge tensor representing all possible parent-child pairs. Most entries are 0, right? False. Only the actual known pairs, like Bob and Charlie, get a 1, true. Storing this sparsely, just as the relation parent Bob, Charlie, is way more efficient than storing the giant tensor, especially as you add more entities or more complex relationships. The efficiency gain is often exponential.
Okay, so that links database-style relations to these mathematical tensors. Got it. But the rules part. linking logical deduction to algebra. That feels like the bigger jump. Observation 2.
This is the core breakthrough, I think. It looks at data log rules. Data log is this declarative logic language often used for databases. So take a rule like aunt xz is true if sister xy is true, Adam parent yz is true. The paper shows this rule is mathematically identical to performing an Einstein summation and Einstein over the Boolean tensors for sister and parent, and then applying one more step, the heaviside step function.
Okay, hang on. Einstein. Let's unpack that functionally without getting lost in index notation just yet. We have sister tensor, the parent tensor. What's the Einstein actually doing with them?
It's doing the database join operation, essentially. But with multiplication, it looks for matches on the shared variable I in our rule, the person who is both a sister and a parent. It multiplies the corresponding entries, which are 1 if true, and sums up the results across all possible high values. So it finds all the paths, all the intermediate i's that could make someone X an aunt to someone else.
And the sum. Right, because X might have multiple sisters who are parents of Z, so the result could be 2 or 3. But logic is just true or false, 1 or 0. So you need something to squash that sum back down.
That's exactly what the heaviside step function HXLU does. Think of it as a simple switch. If the sum from the join is anything greater than 0, meaning at least one path exists, it outputs 1, true. If the sum is 0, no paths found, it outputs 0, false. So this sequence Einsum, followed by step function, perfectly replicates the logical deduction.
Okay, wow. So if that equivalence holds, the entire language just needs one construct, the tensor equation.
That's the core proposal. A whole tensor logic program is just a set of these equations. You have the left-hand side, LHS, which is the tensor you're trying to compute, like ant xc, and the right-hand side, RHS, is basically a series of tensor joins, multiplication, followed by tensor projection, which is summing out any variables like y that aren't in the final result, and then maybe an optional nonlinearity, like that heaviside step for logic, or maybe re-LU for neural nets.
It sounds incredibly minimal, almost too simple, but powerful if it works. What if you have, say, 2 different rules that can both conclude someone is an ant? How does that work?
Good question. If multiple equations have the same tensor on the LHS, the system implicitly sums the results before applying the final nonlinearity. This naturally preserves how logic programming works, where multiple rules can contribute evidence for the same conclusion.
And practically, how would you write this?
You can actually start quite simply. Tensor elements are assumed to be 0 unless defined otherwise. You can use familiar data log-like syntax, like sister, Alice, Bob, or parent, Bob, Charlie, where the parentheses tell the system it's a Boolean tensor fact. And running the program, doing inference, is also straightforward. Forward chaining is just repeatedly applying the equations until nothing new is derived. Backward chaining, to answer a specific query, means treating the equations like functions and recursively finding the inputs needed.
Okay, if that core math really holds up, unifying logic and tensor algebra, then yeah, you could probably describe older AI systems. But the real test, the big question is, how does it handle today's systems, the really complex ones? Can this one thing, the tensor equation, genuinely capture things like CNNs, GNNs, transformers?
According to the paper, absolutely. Section 3 is basically a showcase of this unification. Let's start with a basic neural network, the MLP multilayer perceptron.
Right, the classic weighted sum, the dot product.
Exactly. An MLP layer is just lie tone on my text step. Here, $, is the weight tensor, $6 is the input tensor, and $, is the input dimension index. The join, multiplication, and projection summing over $, is the dot product. That one equation handles the weights and the activation.
Okay, simple enough. What about something with more structure, like convolutional neural networks for images? They seem geometrically complicated.
Turns out, not really in tensor logic. A convolutional layer becomes something like features x, y, filtered x as d, stames image x plus d x, y plus d to h. See how the indexing works? X plus dx and y plus d automatically handle the sliding window aspect. The equation joins the filter tensor with the right patch of the image tensor across all channels. It's quite elegant.
Huh. And pooling layers. Max pooling, average pooling.
Also handled cleanly. It's about projection operators. For some pooling or average, you might define it using integer division in the indices, maybe like pooled xs, yss equals features x, yo, where the $, is your stride or pool size. The summation over the x and y values that map to the same pooled coordinate happens implicitly because they aren't on the left side. And if you want max pooling instead of sum, you just tell the system to use a max projection operator instead of the default sum.
That does sound very flexible. Okay, push it further. Graph neural networks, GNNs.
They operate on irregular graph data, which seems tricky.
G and N's actually map very nicely. You represent the graph structure with a sparse Boolean tensor, say neg xy, which is 1 if node x is connected to node y and 0 otherwise. Then the core message passing step, aggregating information from neighbors, looks like a GNL DEGNN times ZNMND. Here, ZLOA holds the node features at layer L for dimension D. The join with Nozloran automatically zeroes out contributions from any node that isn't a neighbor of Nolers. It just sums up features from the actual neighbors. It's a very concise way to define that aggregation.
Wow. Okay, the big one then. Large language models. Transformers. Attention.
Yeah. The paper claims the entire transformer architecture can be defined with about a dozen tensor equations, creating the query, key, and value matrices. That's just standard tensor multiplication. Joining the input embedding $6 with learned weight matrices WQ, WK, WVWA, the core self-attention calculation. That's an equation like text, softmax, queerup, dk times keep, dka. The tensor logic handles the matching across sequence positions p and p and the embedding dimensions dk automatically through the Einstein mechanics. Positional encoding, too, can be represented using index functions or conditional tensors.
Okay, that's impressive coverage. And just to complete the picture, it also claims to unify probabilistic graphical models, PGMs.
It does. The mapping is very direct there, too. In PGMs, you have factors. In tensor logic, factors are tensors. Marginalizing out a variable in a PGM, that's tensor projection, summing over an index. Multiplying factors together, that's tensor join, multiplication. Even inference algorithms map over. Loopy belief propagation looks like forward chaining in tensor logic, and exact inference on things like join trees maps to backward chaining. So yeah, the claim is this one mathematical framework covers statistical AI, symbolic AI, and neural AI.
Which brings us to what might be the most exciting part, the new things this unification unlocks. You mentioned sound reasoning, but combined with embeddings. This sounds like where tensor logic really tries to fix current AI's reliability issues.
Exactly. This is about fusing the power of deep learning's generalization with the logical rigor of symbolic systems. The key mechanism is embedding relations themselves. So take our parent XY relation again. Instead of just a sparse Boolean tensor, you can create an embedded relation tensor. Let's call it embris. It's essentially a superposition. You compute it like embry J equals parent xy times mbx I times mb joi. You're joining the original sparse fact tensor with the learned embedding vectors for entities x and y.
Okay, so embry becomes this dense, continuous tensor that somehow encodes all the known parent-child relationships in the embedding space.
Sort of, yeah. It captures those relationships within the geometry of the embedding space. Now, if you want to query this embedded knowledge, maybe ask, is parent Alice Bob true? Just you'll compute something like dtext Alice, text Alice, intext, ttext Alice, imtext Bob, dtext tech. You join the embedded relation with the embeddings of Alice and Bob. If parent Alice Bob was strongly encoded in MRO, the result doles will be close to 1. If it wasn't, because embeddings of unrelated things tend to be somewhat orthogonal, the result will be close to 0.
Okay, so we can query facts stored in embedding space. That's using neural network tech. But the really mind-bending part is embedding the rules too.
That's the next step, and it's crucial. You take your logical data log rules, like the ANT rule, but instead of plugging in the original sparse Boolean tensors for sister and parent, you plug in their embedded versions, msister and mparent. The rule itself now operates over these dense, continuous tensors, and you can run inference, forward or backward chaining, directly on these embedded rules and relations.
And because embeddings capture similarity, this naturally introduces analogical reasoning.
Precisely. If the embeddings are learned well, similar concepts, like sister and female sibling, maybe, will have similar embedding vectors. The similarity is captured in the Gram matrix. Simx x equals mbx, d times mbx, d bido. So when you run inference over embeddings, similar entities or relations start to borrow inferences from each other. You get generalization through analogy, baked right in.
But you mentioned control. Reliability. This is where we tackle the hallucination problem.
Yes, this is perhaps the killer feature. The system adds a sigmoid function, tigna t, to the output of each tensor equation. $T here is a temperature parameter, and this temperature gives you fine-grained control over the reasoning style.
Okay, how? If I need absolute certainty, zero hallucinations, rock-solid logic,
Yeah.
what do I set T to?
You set $0. When the temperature is 0, the sigmoid becomes a perfect step function, just like the Heaviside function we discussed for pure logic. This makes the reasoning purely deductive and sound. It follows the encoded logic exactly. The claim is, at T0, The system is fundamentally immune to the kind of logical errors and fabricated facts that plague LLMs. That's a massive potential advantage for high-stakes applications.
And if I turn the temperature up, increase T slightly.
As you increase $2 above 0, the sigmoid becomes smoother. It starts allowing values between 0 and 1. This gradually shifts the reasoning towards being more analogical. It allows the system to leverage those similarities in the embedding space more strongly. You gain more generalization, potentially more creativity or ability to handle slightly novel situations, but you trade off some of that strict deductive guarantee. Having this explicit knob to dial between pure deduction and analogy is, well, pretty new.
And because it's all tensor operations, presumably you can trace the steps.
Transparency. That's another big selling point. At any stage of the inference process, whether it's forward or backward chaining, the intermediate results are just tensors. You can inspect these tensors, see which rules contributed, how strongly, and trace the reasoning back, much more transparent than typical deep learning models.
Okay, the potential seems huge. But let's talk brass tacks, scalability, industry adoption. Why would a big company ditch, say, their heavily optimized PyTorch or TensorFlow setup for this new language, especially if they deal with massive sparse datasets?
Yeah, that's always the hurdle, isn't it? The paper proposes two main paths for scaling this up. The first one is kind of pragmatic, a hybrid approach. You separate concerns, keep your dense tensor stuff, the typical deep learning parts running on GPUs as usual, but treat the very large, very sparse tensors, the ones representing knowledge graphs or logical facts, as relations. And you offload the operations on those to specialized high-performance database query engines, which are already optimized for exactly that kind of sparse relational data. You use the best tool for each job.
Okay, a hybrid. What's the second, maybe more integrated approach?
The second is more ambitious, but potentially more powerful. It aims to keep everything on the GPU. It uses a mathematical technique called Tucker decomposition. Essentially, Tucker decomposition is a way to approximate a huge sparse tensor with a much smaller dense core tensor plus some factor matrices.
So you're compressing the giant sparse thing into a dense representation that captures most of the important information.
Exactly. You trade perfect sparsity for dense efficiency. Once you have this compressed dense representation, you can run all your tensor logic operations very efficiently on GPUs, even the parts that started as sparse logic. There's a small approximation error introduced by the decomposition, sure, but the paper argues this can be managed, and the computational gains are potentially exponential. Plus, the step functions can act as denoisers.
Looking ahead then, the paper paints a pretty grand vision. It suggests Tensor Logic could be to AI what Java was to the internet, the enabling platform. They mentioned backward compatibility, maybe extending Python's Einstein first, but the goal is replacing specialized libraries.
That seems to be the long-term vision, a single computational framework.
Yeah.
And it directly targets those two major pain points holding back AI trust and adoption right now. Opacity, the black box problem, and the unreliability, the hallucinations, especially when trying to get LLMs to reason logically. If you can offer guaranteed sound deduction at T0, that unlocks AI for areas where mistakes are simply unacceptable: medicine, finance, critical infrastructure.
Okay, the focus has clearly been AI. But for listeners maybe working in scientific computing or other complex modeling fields, is there a final provocative thought here? Does it go beyond AI?
The paper definitely hints at that, because tensor logic provides such a direct mapping from mathematical equations to executable code. It could potentially be useful across scientific computing in general. Just write the equations, it runs. But the really mind-bending idea, the truly provocative one, it's about making computation itself learnable. Think about almost any program. It has control flow, right? If statements, loops. These are often based on Boolean conditions. What if you represented those Boolean control decisions as tensors and then relaxed them into continuous numeric tensors? And what if you could then learn those control tensors through optimization, making the program adapt its own logic? The suggestion is that tensor logic might provide a foundation for doing just that, making any software potentially adaptive. So maybe it's not just a new language for AI, maybe it's a glimpse of a new foundation for computing itself.
A learnable foundation for all computing. Wow. That definitely moves the goalposts way beyond just fixing LLMs. A truly staggering thought to mull over. Plenty for us and you to think about.